Ellie, you got to come up and start over. So thank you, Ellie, for doing that. So Eva and I are actually preparing for a webinar next week about visualizing finance data. And as she and I were going through materials, we were trying to look for good examples. Tableau has a website dedicated specifically to visualizations for finance. And this is the first one that I saw, which I didn't really particularly like very much. So I decided this morning to give this a makeover and show it as, is my screen still sharing? Okay, there we go. All right. Hi, Simona. So basically this is supposed to show, it shows net sales and net profit compared to profit margin across quarters. It's kind of messy. Things don't line up very well. There's way too many categories. And I wanted to create kind of a visual income statement. So what I've done is I've created this version instead. So let me switch to full screen. And instead of it going kind of, so that one was sort of all over the place, I kind of took the important stats that were inside of the table at the bottom. So gross sales, discount, kind of the income statement. And I made it in a Z pattern. So you go across the first row and then across the second row. So everything is in order. And the way that you read this is the bars that you see. So if we just focus on gross sales, the bar at the top is year to date. And in this example, it goes through May 2015 versus 2014 through May. So same period prior year. So that shows that you're up in sales versus prior year. So blue means good, orange means bad. But what's interesting is if you look at the month over month variance to budget, so the line below that is current year and prior year by month, and it actually shows where you are compared to the budget. So what's really interesting about that is it shows you're not way below, but it shows you're below budget, yet you're over prior year, which means that the person doing your budget really doesn't know what they're doing. So you wouldn't, but it's an interesting, it gives you interesting context because you can look at, so you're up over prior year, but yet you're still down versus budget. So either your goals are really high, your goals are obviously much higher this year than they were last year. And some of the bars, while they extend past the reference line for prior year, for example, discounts is in orange because your discounts are higher than they were last year. You actually would want your discounts to be lower versus prior year. So that's one where the bar, you want it to be below the line. So I tried, instead of having it pointing in the negative direction and looking kind of weird, I guess that would be a debit, right? Yeah, that'd be a debit in an income statement. I wanted them all kind of going the same direction. And what's really cool is if you view this, let me see if I can view this in I'll view it in what it would look like if we look at it on a phone. So let me refresh the screen. Hopefully it refreshes. Let me refresh. No, it's okay. I just need to refresh the screen. Okay. Where's my browser window? Where is it? Where'd it go? Now I'm stuck. How do I get out of? Oh no. How do I get out of the? Huh?
Oh no.
Well, no. Okay, sorry. What I want to do is I want to get out of. I want Chrome to go back to. Shit. How do I go back to the view that isn't maximized? Anybody know? Escape? I tried to, exit full screen. There we go. Okay, there we go. So what I'm going to do is I'm just going to switch this to, actually I think that's what this tool does here, mobile browser view. And if I want to look at it on a phone in, let's say 375 by 667, which would be a standard iPhone size, it'll now render on the phone, hopefully, and you can see how it looks. Come on. So instead, when you're looking at it on a phone, it's a nice little scrolly top to bottom kind of version instead. So anyway, fun thing to kind of build today, and great having feedback from people in the room and also from the greater Information Lab team. So thank you for that. All right, any questions on that? This would have been perfect to show the lady next to me on the train. All right, it's on server now, Ravi, so you can show her. Go run back and get her. All right, so next up, we have Elena. So let me present her screen share. Attendees. Elena, make presenter. You got it?
Sure. Okay. There, the moves. Okay. Okay. Hi there. My name is Elena, and today I'll talk to you about basics, table calculations, and calculated fields. What?
Say that front.
Okay. So we will look at table calculations and calculated fields, give a few examples of both, talk about how and where they're computed, and talk about row level and aggregate calculations. And we'll close up with the computing direction. First, we will look at the differences between table calculations and calculated fields.
Is this PowerPoint?
Yes.
It looks really nice.
I have a board one, but I think that one's even worse.
I'm just messing with
Okay. So after me, Mina's going to present a little bit more about LODs and table calculations, and she will go more in depth with the computing. Okay, so where are table calculations and calculated fields computed? As you can see here, we have a view of how Tableau works when reading from a data source. At the left, you have the software, and on the right, we have the data source. So Tableau uses SQL to read the visualizations, to read the data. And in the middle between the data and Tableau, we have the data interpreter, which merges the two programming languages together. So when Tableau connects to the data, it creates a view with what we want to be in the view. So it uses the table, the measures, the dimensions. So when we create a table calculation, the calculation is created in the view from what's in it, and stays within the view and doesn't transfer to the data source. When we create a calculated field, we create the calculation within the data source, and it creates a separate column with the values in the calculation. So basically, you see they are computed in different places within the system. This is basically the same thing. Okay, so table calculations include the quick table calculations. Let me just open that up. Yeah, so we have the usual running total difference, percent of total rank, and if we have a time dimension, we have the year-over-year growth. These are the most common, the most common used calculations in analyses. So the table calculations are cached within the operational memory in the computer, which Tableau uses for to run. If we create a table calculation and then we want to view it in another view or within another worksheet, we can actually transform the same thing in a calculated field. So you can do that easily by just dragging and dropping it into the left, into the measures, and it will transform into a calculated field. For calculated fields, there are many ways to create them. So we have, let me just go back to Tableau. This is why it's useful to actually have it in Tableau. Yes. So you can create an ad hoc calculation by just pressing into the column to rows shelf. We can create it from analysis down here, create calculated field. We can create one from this drop down, from the little arrow.
Jeremy.
Okay.
Jeremy.
There's up to 5 ways how we can do this. Just go back to this. So here are some examples quick table calculations, and now we will look at some examples for the common calculated table calculations. Okay. So we will look at lookup, Zn, as well as the if null and is null, the first and last, the rank and the index. So first we'll look at lookup. This is a calculation I didn't know when I initially started my analysis in Tableau. So what it does, it basically looks at what's in the view, what's already in the view, and you can actually shorten the calculations that you do with this function. So in this case, we're looking at the years of the order date and the customer ID. So we're basically counting how many customers we had for each year. So with the lookup, if we put it in this calculation, Tableau will immediately know to calculate what's in here. And on the end, we say -1, so it calculates the difference from the first to the second year. And
So this is looking at essentially year over year. Is that correct?
Yeah.
So it's saying, look at your customer count. So in other words, if you're standing on 2015, the first part of that calculation will return 2109, because that's your count of customer ID. Is that correct? So this first part here
okay.
will return
Yeah.
2102.
Yeah.
Sorry, I said 2109.
The second one,
And then minus, so that
Yeah.
lookup is basically saying look backwards one year, correct? Okay. Minus 1993.
-1, yeah.
Okay. Gotcha.
Okay.
So we could look forward if we wanted to.
Yeah.
Yeah.
With that, do you want to go back there? With that one, Andy, can you just show the last year? If say you had a parameter that said, I want to see from 2016 1 year back, and you input that formula, could you just show 2016?
Well, you could either how would I do it if you?
Because I had this problem the other day, and I kept getting the table out.
Yeah, you can. You just need to. Well, you would still have to keep year in your view. You can't filter it.
Yeah.
Because year is what's being used in the lookup table calc there. So what you would do is you would, I would actually right click on 2014, 15, and 17 and choose hide. And that basically just makes them transparent to the user. They're still in the view.
If you had a parameter that would say you were switching between the years.
Oh, you wanted to decide which year to
so
show.
that, yeah.
Yeah, you could do something similar to that. Yeah.
Something similar.
Yeah, so if you had a parameter that said that had the 4 years listed, you would say something like if the parameter is equal to the year of order date, or just say parameter equals year of order date, that's going to give you a true false.
Yep.
And you can put that in there and just hide the falses.
Brilliant.
Yeah.
Okay. Next are the last and first functions. So what they basically do, they assign numbers to our dimensions, and the difference between them is that first goes from the first number that we have and counts, assigns the numbers in a minus scale downwards. Last does the opposite. It assigns the numbers from the highest to the lowest, ending on the last value that we have. So these are useful if you want to show, let's say, sales over time, and you want to always start with, let's say, the last 6 months. So you can say last and then 6, and you would be able to filter to those months, especially with live data. Another way to assign numbers to our rows are rank and index functions. So basically rank,
See where you are.
yeah. Basically rank will look at the measures, the value that each dimension has. For example, we'll rank the rows by highest sale or ascending or descending order. While index will not look at the measures, but will just assign how they are sorted in the view. So this can be useful for, let's say, a manual sort.
Mm-hmm.
So what will you use, or what team are you on, is usually how you like to show the data. Do you like to sort? Do you like to keep, let's say, regions sorted manually?
So an example of that is you may have profit in your view, but you might want to use the rank to sort them by sales.
Yeah.
Or something like that, yeah.
Next, we'll look at functions for dealing with nulls in your data. Here we go. We have three essential functions for this. That's the Zn, that's at the lower right, the lower left. And then the fnull and isNull functions. So initially, you'd know that they deal with nulls and zeros, but what's the difference between them? So Zn focuses on measures. So it looks for null values within a measure, and it replaces them with a zero. Well, if we look at ifNull and isNull, they deal with dimensions. So they look at null values within dimensions. The difference between these two is that isNull just looks if there is gives us a Boolean result. So basically, it's true we have nulls or false we don't have nulls. It does not replace them with anything. If null looks at zero, looks at nulls, and then gives us the option to replace them with a text or whatever we want. So basically, we can say if it's if null, then give me NA or unknown. This is the same thing. Okay, now a few words about row level and aggregate calculations. So when we're writing calculations, we have the choice to go on a row-to-row basis, or to view the whole data as whole. So if we go with the first one, with row-level calculations, we can, for example, calculate a profit and sales ratio, like the example here. So in this case, you see they're disaggregate. If we go with an aggregate example, we would have a sum or count or average sales, and we will look at the whole table of all the rows that we have in the view. Just one thing, where is it? Okay, an important thing when writing calculations is to remember that we can't mix aggregate and disaggregate measures because we won't be able to get the result. Okay, computing direction. This is how this essentially will look at how the calculations are computed within the view. So for this, I'll actually need to draw a table. Okay. So we have our rows here, our columns at the top. Let's say if we look at customer ID, and this would be, let's say, product subcategories, furniture, technology. That would be it. So we would have the customer number. I'm sorry for those who are online who can't see. And we would have some values here. So if we activate our totals, we can see what are the end values in our view. And here we can have totals. Second. And here is the options where we can pick whether we want the calculation to be computed by table, by pane, table down, table across. So basically, we have the table down option. It will look at the calculation like this. And then when it comes to the end, it will stop computing and start for the next one again and compute from 0 down. If we have a table across, it would take the rows, compute by the rows, come to the end, and then start the next row from a 0. So we will get values for the sums of each row. The table across and down option will be, we will go again across to the end, and then Tableau will remember this value at the end and use that one and start from it when it starts for the next row.
So it goes in like a Z pattern.
As a Z pattern, yes. And the same principle if we're going down then across. It goes to the down of the table, remembers the value, and uses the same value and starts from it on the next column. Now what happens when we have the pane option? The pane basically divides our view in different panes, such as, let's say, categories of, if we have here plus subcategories. If we have something that looks like this, and we have value here and here, this will be a subcategory pane for furniture. So here we also have pane down, calculates here, stops, starts again. Pane across, starts from 0, gets to the end, calculates, and starts from 0 again. And the same as with the table, it will go for pane across then down, it will calculate to the across, and then go on a Z pattern and continue on from there. So in this case, I don't know if I have options for specific dimension. Yes, I do. This is the third option that's useful if you want to calculate your calculation for a specific dimension that's in the view. So how this works is you go from bottom to the top, and you say for each you deselect. So for each, if null is null. It's not a very good example in this case.
Why don't you build another? Do you have Superstore in there? Just build another example.
It's not open. I'll have to.
Yeah, you have it open.
Oh, I did. Okay, sorry about that. Okay. Sorry. You can see what I'm looking at. Okay, so let's have a look at
Just do category and subcategory.
product category. Okay. And subcategory. Let's look at sales. Let's look at percent of total. Compute using either table calculation, specific dimension. So for each, in this case, we would like to look at subcategory. We can untick subcategory and say for each subcategory, compute by the category for a percent of total. Now this is a little bit tricky to actually read, but you untick the one that you want to be your first value, and you're computing by category, which will be ticked. Let's have a look.
So what if you switch them around?
It would be for each category, compute by a subcategory the percent of total.
Right.
Or you
So
can
this
go
is
for
the same. This would be the same as pane down then.
Yeah.
Yeah.
But you can more easily view the dimensions that are in the view.
Right.
Okay. So here you see it computes by each category as we left it on that part. Okay. So that's my presentation. Any questions?
No, good job.
I have one. Is first and last, are they indexed? Are they a different variation of index?
Sort of. Yeah, they all three of them just count.
No positional.
Index starts at 1, and index always starts from 1, and it's just the order that you are within the however you define, however you tell it you want it to count. First tells you how far you are from the first one. Last tells you how far you are from the last one.
It's a shorthand. If you want to count backwards, rank index. rank index inside the rank account.
At point you make rank index ascending and then it's forwards again.
Yeah. I need a while to digest that.
That's a table calc inside the table calc. All right, good job. Well done.
Thank you.
Next up is Mina. So let me give you control, Mina. No questions, right? I didn't see any questions.
Okay, just have to hit the mouse really hard. Okay. Hi everybody online. Thank you for joining us on your Friday afternoon. I don't know why you put yourself through it, but hope you can at least enjoy or learn
Maybe
something.
they're in the US and it's early in the morning.
Yeah, well, I would think so. But, yeah, I'm Mina here. I'm here to talk about level of detail calculations versus table calculations. You kind of already got a bit of a taste of it, and Elena went into a lot of detail that I won't cover here, but I might go over some of the things she has already talked about, but in my own way or in a slightly different way. And maybe it reinforces it, maybe it confuses you. Hopefully the first, not the latter. So, running order, going to go through just some concepts, some core concepts that I'm going to use throughout to explain what exactly I'm talking about when I say data and view and measures and dimensions, just so that your understanding is what I'm thinking when I'm saying it. Talk about, but you can use calculations to do the same thing. Why are we using one or the other? What are the calculations? Break that down into components to explain them. It's better to understand them because they're so complicated in little parts. So I'm going to break them down. Why is it necessary to use them? Like, why do they even exist, I guess? And then a couple of cases. So we're going to open up Tableau, show the case for LOD, which is not easy to do in a table calc or any other kind of calculation, and then a table calculation, which is not really easy or possible to do in any other calculation. Then going to wrap it up with pros and cons of each of the methods, more from a kind of practical sense of when you use them in a business. And then a little bonus, which is if you have table calculations, how you can actually translate them into a level of detail calculation. And that is only for window calcs. So, and I should also clarify in case you've already noticed, is that I will refer to level of detail calculations as LODs and table calcs, or table calculations as table calcs, because I'm either efficient or lazy, once again, depending on how you see it.
Even mix them on that page.
Yeah. So once again, sorry for the people on stream who aren't going to be able to see this, but I'm just going to quickly draw out for those here.
Whoa.
Sorry.
I wonder if I could turn on, I probably can turn on my screen, my camera.
So I'm going to draw out here. We're going to call data. Okay, and then we're going to have a little section in the middle, and then we're going to have a bunch of crosses that are going to represent the Tableau icon. And each of these are going to have their own lovely little table, and I'm really awful at drawing and awful at writing, so please bear with me.
It's backwards too.
I know, I've done it the opposite way around. For people on stream, I've done it the...
On the camera, it's backwards.
Oh. Oh, you put a camera on. Oh, great.
No pressure.
No pressure. So, what I refer to in here is the data and the view. The data is what you actually bring in to Tableau. It's when you go to the data source and you see that table there, that's what I'm going to refer to as data. View is when you actually go into a worksheet and you're creating a chart. That is what you see as the shelves and the marks. That's what composes of the view. So I can go ahead and just quickly show you. So all of the columns and the rows and the marks and this view will compose of the view. And this is what I consider data. It will become important in a bit when I try and explain the differences between LODs and table calcs. So let me not skip ahead. Ooh. Okay, so I'm going to go ahead and, I guess I can go ahead and jump in this. Dimensions and measures. Why is it important?
Are you done drawing?
Yeah, I'm done drawing.
Okay.
For now. I'll draw a bit later. just to be really jarring. So dimensions in regard to the view is whenever you drag a dimension in, it decides the number of marks in the view, and it also decides the number of rows for the table feeding the view. So if you have 1 million rows and you have the US states, you drag the US states into view, how many rows do you expect in that view table? 50, yeah, exactly. That should be how many marks there are as well. Someone give a different answer? Well, yeah, if you're being technical, maybe.
I was listening.
There's only 56.
Okay, okay. So
It's not
then,
a state, it's territory.
so then I've qualified here continuous measures will give values to each of those marks. So you'll still have the 50 marks. If you drag a continuous value in, like let's say some sales, then you will get a value for each of those 50 marks.
Yep.
In regards to that. So the reason I'm explaining dimensions and measures is because level of detail calculations and table calculations both perform aggregations, and it's important to understand that when you drag something into view, it's going to aggregate, but then also when you talk about LODs, they're going to aggregate. So I've also included this little table here of what the data would look like, and when you drag something into view, so let's say this is the state of the sales, this is how like over 25 rows become one row, and all of these values become one value.
Mm-hmm.
And this is because it's doing aggregation. And for anybody who doesn't know what aggregation is, I mean, we've been drilling it into data school on and on. But once again, aggregation is how do we somehow like compile all of these values into one? So you can do it via many methods. You can add them up. You can average them, which is basically adding them up and dividing by the number of them. You can do other things like standard deviation or medians, different kind of computations. But there's lots of ways you can do it. And it's just a matter of trying to consolidate all of those into one record. Okay, so that is the first.
Good explanation.
Well, I'm sure I'm going to mess something up later, so it's probably pretty good that I'm not doing too bad yet. So I know I'm going to mess something up later. So I've also kind of tried to break down calculations now. So we've kind of already talked about aggregation. We're going to talk about calculations particularly. So Elena's done a good coverage of the regular calcs and the aggregation calculations. So once again, regular calculations are if you create a calculated field, what it does is at your data, it looks for that value on a row of sales. And it's going to look for that, take it, find profit on that same row, and it's going to do sales minus profit. And that's how that calculation works. It will give one value for that row, and it will do it for every single row.
So it's appending a column to your data source.
It's appending a column, and it does a calculation for every single row on that row. So aggregation calculations are a bit more interesting to explain. So it's going to add up all of your profit and sales, but it's going to do that based on what's on the view. So once again, why it's really important to understand what view is. So if you have states in view, it's going to sum up for each state all of their profit, sum up all of their sales, and then divide profit over sales for each of those states in view. Okay, and then here's our two important ones for today, table calcs and LODs. So they already kind of have an interesting little syntax. You can see it's got here, I'm focusing on the window sum sales, and then we have a fixed state sum sales. They're not really supposed to be the same measures, just in case anybody's wondering. But the kind of window calcs go a little bit bold to maybe indicate to this, and the LODs have curly braces to indicate what they are.
Mustachios.
Or mustachios, as Andy Krieber likes to refer to them. I don't think I could live with that, but okay.
You only have to live with it for 4
Yeah.
months, just 4 months, and then you can switch back.
So we have these 4 different types of calculations, and it's like, oh, cool, so they do different things, but actually they can all do exactly the same thing too. So, so I had a bit of fun, and I took all of the states, and I did sum sales with regular sum sales. I did sum sales inside a calculation, or it's exactly the same as sum sales, but inside a calculated field. I did a window calculation, and I set the configuration up so that it basically did no real aggregation, so it did essentially the same thing as sum sales. And then I did a fixed with the equation from before, so I can show you. I just did.
So it's the same 4
Fixed
measures
state
that you used here, or no? It's the table calc and the LOD are the same as the previous one, right?
I don't think these are actually the exact. I didn't put those in. No, that would be too smart of me if I actually put the exact calculations I used here. No.
Okay. So is that state sales?
So this is states I put alongside. I just haven't labeled it for space reasons. And then you can see each of the values are equal across, despite these being 4 different methods. And just to prove that I'm not cheating, it is 4 methods. I'll go ahead and show you.
Ooh.
So let's go to sheet. Okay, so We can already see that one of them is a table calculation because it has a delta symbol, or the little triangle, however you want to think about it. We have an aggregation here, so
It
that
needs a
tells you
name.
Pyramid.
It needs a name.
pyramid. I like delta, but I mean that's my bias. So you can see there's an aggregation. So that tells you that's an aggregated calc.
Upside down carrot.
There's my regular calc, but it's been summed into the view because I brought it into view. And then I have a fixed, which, for the sake of everybody here, once again, prove that this is possible. It is indeed a fix. Okay? Cool. So if they can all do the same thing, I mean, why do we need to know all these different methods? Like, what's the point of learning 4 different ways to do the same thing? Because they have places where they excel. They can do the same thing, but you shouldn't use them for the same thing. So how you can understand table calcs and LODs as being different from regular calculations and aggregations is quite complex, so I'm going to break it down. So first of all, it's kind of what Elena said earlier. Part of it is about location. So where they're calculated. LODs, it's been drawing for the sake of people online, are calculated underneath the data. And in the view, we have table calcs. Okay? That means it has different implications for what exactly it's calculating. You could put like window sum sales as a table calc, or you could do fixed sum sales. They would not return the same thing. They're not computing the same thing. It really depends on how you set the configuration of them up. So what do I mean by configuration? That goes back to right at the start when I mentioned dimensions. So dimensions.
So I think that first sentence you have there in your table calc definition is really good.
Yeah, so this is what I mentioned here and earlier, is that they're performed solely on the data in the view, and then level of details are summarizations at the data level. And then the little complex part is that in LODs, they summarize at the data level, and then they join back to what's in the view based off of the dimensions that they've made in the table. And then there's some little interesting parts where the aggregation of the LOD and view will then mean different things. So you have to just understand what it's doing. And there are the dimensions that are important for LODs also depend on the type. And this is something that's going to go into more detail with a few of the data schoolers later. But basically, fixed will specify entirely what it's looking for at the data. Include and exclude will then look at your view, see what dimensions in the view, and then take that into consideration depending on what you put in your calculation. In comparison, table calcs have a little interface, and you have to decide based on that interface what it is calculating. So yeah, it sounds very abstract. We're going to go into practical examples. What does it all mean, kind of thing. So I've kind of already started on this. Where they're computed is one of the few things that distinguishes how they're different, but there's others. So how are they computed? I've started to go into LODs is computed at the data level and joins back. Table calculations have this kind of interesting syntax. So let's. Oh yeah, here's for the benefit of anybody online. I've kind of done it, and I haven't gone back into presentation mode. Silly me. So here's for the benefit of people online. This is what I've pretty much drawn, but nicer because I can't draw. So here's how they're computed in terms of their syntax. Now it looks kind of crazy. So the first part on the left-hand side, the LOD dimensions, that means whatever comes after the fixed or the include or exclude statement, that is your dimension, and that is exactly equivalent to partition, which is also exactly equivalent to for each, which is the unticked boxes. So what that means is this partition is Tableau's old way of computing table calc. So most of us don't use that, but there's a few people who might still use it, so I included it. For each is the new method. So if you untick a box, Andy Kubel, that's why his face is here, likes to refer to it as for each. So I've included it on that. This last bottom section is not exactly equivalent, hence I've not put an equal sign, but it has to do with partitioning. These two features have to do with partitioning, but they're a bit more complex and not going to be in the scope for this presentation. But there's some good reads online about them. So the right-hand side is a bit more complicated to deal with. So we understand dimensions, we understand grouping by, we kind of went through that in a lot of detail. But the addressing, which is these kind of things that you tick on the second level, you can see compute by ticks boxes. What does that really mean? Some people like to think of it as like ignoring, which is really kind of interesting way to think about it. Or just that you are doing one calculation first and then another. So for example, if you do a table calculation with state and city ticked, or in this case I think I've done city, postal code, order ID, that's going to be a nested like LOD. That's the equivalent. Is you have to nest something to get those ticks, and then the untick is the outer.
Mhm.
So it's really weird. As I said, I'll do it right at the end to show you how you can easily translate them. But basically, if you want to see what the equivalent of a table calculation to an LOD is that the ticks will be a nested LOD, and the unticked,
the inside part, right?
Yeah.
So you read them inside out.
Yeah. So it's a nice little sandwich, weird way of thinking about it. So they have different ways of doing this kind of partitioning, addressing, or separating for each. And what it means is that you can do slightly different things calculation-wise because of the fact that you have this at the level restarting every. You can do a bit more weird kind of considerations in organization. The other thing that's really important, and I'm not sure if I have it next, can't see my slide, is that table calculations also do more than LODs in regards to their functions. So you could think about it as the window calculations are the equivalent of LODs, but that's not all that table calculations are. So table calculations also have, as was mentioned, indexed and last, and these kind of more positional calculations, and then you also have moving averages and those kind of things. You can't put comparable.
They're almost aggregates on aggregates, right? Then
yeah, both
table calcs. Yeah.
Both table calcs and LODs can do aggregates on aggregates. So this nested is an aggregate on an aggregate, and you can do window sum and window average on anything, right? But what makes table calcs a bit more unique is that they can do multi-rows. That's what makes it really definitively better. So yeah, here it is on this slide. So as a general kind of use case, we tend to say that LOD should be used when you need to compute something using something outside of the scope, and that table calculations are just trying to do further computation on something in the view. So you want to do another calculation, but just using what is already there. But that's not even necessarily true. I find in practical cases, you're solving a problem, and whatever makes more sense to you, you're going to use.
Sure.
Regardless of what the philosophy is behind using table calcs and LODs. And the best way to kind of get used to how you can use and strict Tableau is just to practice and use them.
So I guess with the first sentence there, I guess another way, so the second sentence, the table calcs. So those are better to use if you had exactly the dimensions you need in the view already.
So yeah,
right?
so I don't know, you want to do, you have product name in view and you have state in view, and you want to find, for each of the states, you want to find the average spend per customer or something. Or no, so yeah, I should have said customer name and states. So you can do that with a table calc as well, even though a lot of people might solve
both in the view.
As long as they're both in the view, you could still perform that calculation. But it might just be more natural for you to do it with an LOD because you can think about it in that building up logic.
Sure.
Because LODs are very bottom up and table calcs are more top down.
Mm-hmm.
So both of them also try and solve these problems. But as I said, table calcs are better at solving the problem of multi-row. So you want to see the previous year compared to the current year. You want to do a running total. You want to do an index or something. So multi-row logic is much better using table calculations. In fact, it is almost impossible with LODs. So computation requiring different levels of aggregation, that's possible by both, as we just explained. As long as you have it in view, you can do it with a table calculation.
Yeah.
But for a lot of people, that logic is easier to think about in LODs.
Mm-hmm.
And then as I explained the last one as well, aggregating an aggregate, you can do that with both. So as Elena kind of, I think she might have touched upon it, is that what would happen if we tried to do some sales normally? Does anybody know what's going to happen? Someone should know.
Tableau
It's going to go
down.
wah, wah, wah.
So for anybody who doesn't know, if we try and do create calculated field with a regular expression, we have sum sales, okay? We want to find the sum of that for some reason in view.
So you almost like you want the grand total,
Something,
right? The sum
something
of
of
the
it.
sum of sales,
We
right?
were trying to find some sort of sum. Okay, Tableau then gives you this error. It's already an aggregate. You can't aggregate it. which is true for regular expressions, but window calcs and LODs can get around it because of the fact that they have this logic built into them. Because you can decide a dimension to do a calculation on, you're saying, okay, in view, you're calculating some sales. So you're saying, I'm aggregating to state. But because I have an LOD, I can say, I'm aggregating to state, but then I'm aggregating to country. You can't do that because with a regular expression, because it's just taking what's in view. If the dimension is state, it will take state. You can't do any more than that. That might be a bit unclear, and I'm not sure if you guys get it.
So is that like, because you use an LOD, you're saying, oh, I'm fixed on this set of data, which is part of the data, therefore you can aggregate out of it because there's more data outside of it.
Yeah,
LOD creates like a temp table, essentially.
Yeah, but even more than that, it's the ability that you can specify dimensions in table calcs and LODs. You cannot specify what this is summing across. So the first sum will
In a
take,
regular expression.
Yeah, in a regular expression. So in this, it will take whatever is in view. You're summing sale of state. But how is it supposed to know what the second sum is doing? There's no ability to specify a dimension in a regular calc.
At the moment, the country would.
No, it wouldn't. It would be whatever this would be. It can't even run. So like if I
yeah, it depends. So if there's no dimension.
So doing Windows of sum of sales would be the exact same thing as putting the grand total. As in it would just
Let's
take
say-
the sum of all the things that are in the view and just give you the total.
So if I put city and state, I put some sales. I could have just left it some sales. So when I do this, okay, well, yeah, I'm not going to sort it, but forget it's nested. You get what's at the level of city. You can't tell it to say, I want to take the state, because it's going to just automatically just aggregate to the lowest level in the view. The only way to do it is to write a Windows calc or an LOD. So I could do window sum, sure, sum sales, and I'm just going to call it sum. I have to, just in
Get too many
case,
sums in there.
just in case I can't find it, it's a really common problem.
So initially, it's going to do what? It's going to take the grand. That's the grand total, right? Because it's
So-
a table down.
Yeah, so it's saying it for everything. So I don't know, if I wanted to say for each state, I'd untick state and it should do it.
Yep.
There. So now I would say I'm finding the sum across this for each state, ignoring or like adding up all of the cities, depending on how you
Right.
want to think about the addressing part of it. But once again, the reason you can't do that with a regular calculation is there's no ability built in to specify extra
What the
dimensions
dimensions are, right?
to aggregate.
Yeah, good point. Yep.
It's just one of those kind of logics that happen and you don't really understand because Tableau is doing it all for you. The view decides the dimension. That's why you can put sales and it sums it.
Yeah.
But when you try and further sum it, you need some other ability to do that. I hope it's a bit clear. I know it's
Yep.
quite
That's
difficult.
good.
It's difficult to explain, let alone understand. Right. So yeah, let's go ahead and build the two fun examples. We can get off the theory for a bit. Theory is a bit hard to understand and take sometimes. So maintain percentage when I filter a dimension. This is a real problem.
So this is one Marcus is doing?
Don't want to do it.
I'm not going to do a beautiful example like Marcus's later. Marcus is going to have a very beautiful.
Marcus has got great ones.
I'm doing a really boring one, so I'm just going to do. So I want to have. I want to make a map of all the states. So let's go ahead and do that. And I want to see. I want to see the percentage of sales for each state over the of all the states. So I'm going to say sum sales, and I want to divide that by, in brackets, sum sales. And then it's not going to like it because I have an aggregate and a disaggregate, so I'm going to sum that. Weirdly enough, LODs are treated like disaggregates when you use them because of the fact that they're now adding a value at a row. So we're going to call this percentage. I'm going to toss that onto color, and then I'm also going to toss it onto label, and it's going to be awful numbers, and I probably should format it. Why not? Okay. Everybody here.
Your OCD's kicking in.
For everybody's eyes, so they understand that it's the same. Oh God, it's awful. Oh God. Okay. Well, anyways, we'll just take the case of New York, okay, guys? Trust me. Have faith. So what is it going to be? East?
Yeah.
Let's go ahead and say east. We filtered and east is still 14%.
Mhm.
Normally that would only compute the
So if
percentage.
you did that as a table calc, if you change your, can you undo and put it back to the, so if you open your calc back up, your percent calc.
Yep.
And if you change the bottom to be a window sum of the sum of sales, so get rid of your LOD.
Now we got our fun numbers back. Oh,
And
God.
that's going to give you, so you need to tell it how to compute.
Because that's going to table down.
So you do it at the, you want to do it at, so check state.
Yep.
There you go.
That's
So
what I
now
was
New
trying-
York is 14% again, right? But now if you filter to region,
Let's find the region. Boom. And we want east. And there we
New
go.
York will not be 14% because it's only
Yep,
basing it
four-
on,
State, isn't it?
so it's 45% of the east. So that that's a good demonstration of how
Oh,
LODs
no.
ignore the calculation.
I need, well, it's okay. Well, we'll make it through before this laptop dies, hopefully. Oh, don't go ahead, Okay.
It's a spoiler.
Spoiler alert. Okay, and the next one is once again the best part about, or at least what I find to be the best part about table calcs, the multi-row kind of computation. So we're going to go ahead and toss in order date. We're going to do it by week because we want something quite granular for this example. And I want to toss on sales again. You're really going to get bored of the sales, I'm sorry. We're going to go ahead and do a moving average. This isn't quite solved my problem because I wanted to get rid of my noise with the moving average, so I'm going to go ahead and just edit it and maybe say, I don't know, I want the past 10 weeks.
Ooh, is that the last 10 weeks?
Sorry, I'm sorry.
That's
I
11
so.
weeks.
Fine, we'll do 9. There we go. OCD alert is really kicking in. Okay, there you go. So these are not easy to
Looks like
replicate.
a mountain
across-
range.
It's really not easy to replicate what this has done in any other calculation besides a table calc. And the same for the LOD example. That's why they're really useful if you want to answer those kind of questions. What is this percentage of the total? But I still want the functionality of filtering to a region. Or I want to see this, but remove the noise. Okay, let's get rid of these. And nearly done, guys. Nearly done with all the intense theory. So this is like the easy fun part. Pros, cons. So table calculations, really easy to start computing them. You have that, as Lynn showed you, right click and you can make a quick table calc. It's easy to change what it's computing across. You get to see what it's doing. It's quite easy to get going with it, and it's quite easy to get like things you wouldn't normally know how to compute necessarily, like, I don't know, percentage of this and that. It's quite easy. And it has more functionality, even though people might think of level of detail as having lots of functionality because you can build it up. It actually has more functions and can do more kind of complex logic than an LOD. But the problem with table calcs, and I'm really sorry I keep forgetting to put it back in the presentation, is that they break really, really easily. If you take anything out of view, you hand over your work, somebody tries to play around with it, they break it, oh no, they don't know what was on it, unless somebody wrote a huge document.
Also really hard to copy.
Yeah, so it's really not scalable. It's really not easy to do. And there's also, at least in my opinion, you have to spend more time to check and validate that the value you get is actually correct. So level of detail calcs. On the pros I've got quite a lot, but maybe I'm biased for level of detail calcs. They're easy to reuse. So if you have a calculation of per customer and you want to scale it up, you can just change the field. It's easy to scale because you can hand them over. That calculation is always that calculation. If it's a fixed, because it's always calculating from the data, so you know that it's doing what it says it's supposed to be doing. As I said, it's easy to share. And you can use them as dimensions, which is an interesting part. So if you want to count the number of I don't know, orders per customer and then put that on an axis and make a histogram. You can do a lot more kind of cool tricks with that.
Would that be a dimension?
Yeah, I said dimension.
Is it a histogram?
You can, as in the bottom, if you do 1, 2, 3, 4, 5, split it up as columns, and then across you can do the count number of records or whatever it is that you want. So you can make as precise and weird of a calculation as your company needs you to do. If they want some really particular calculation, you can make it. And then also the cool part is the fix can ignore filters. So as we saw, it can maintain that percentage.
One clarification: when you have your can use LODs as dimensions,
Yeah.
you can use fixed
Fixed
LODs.
is, yeah, so
as
same thing. So
dimensions.
fixed for the dimensions part and fixed for the filters part.
Right.
Only valid for fixed on those two. So then the con is the biggest con that anybody ever quotes about LODs, which is that they are slow on performance. But I think the caveat to that is they are a lot better because Tableau has built a logic in where it decides if it needs to query. Like it sees, do I need to do this query? So maybe if you put fixed state sum sales, if you already have state and sum sales in view, it wouldn't perform that extra query that it would need to. So it consolidates it and makes it a lot more efficient.
Yep.
So yeah, they're not as bad as they used to be on performance, and so maybe there's more incentive to start using LODs now.
You're clearly on Team LOD.
So,
Okay, bonus time, guys. This is really, really simple and really cool, and I played it hopefully really simple. So on the right-hand side, we have our table calculation interface. On the left-hand side, we have an LOD. Oh no.
Yeah, you're good. You're good.
you're all right.
I'm good.
Plenty of time.
We got
Quick,
plenty of
quick.
times.
It's already
So
6
whenever you're
o'clock.
fixed on a dimension, as kind of was specified before, is the state is unticked. And the sum sales, which is what you've embedded in your window sum, is the same as what you put on your right-hand side of your LOD. This is a trick that only works with the window sum and a sum, and I'll show you why for the next one. So with any other window calc, you have to do this. So once again, your dimension is unticked, but you have to nest an LOD.
Oh, for a window average, right?
For anything, any average, min, max, standard
Yeah,
deviation.
but not a window sum, right?
Just not the sum.
Okay.
The window sum would actually work exactly the same as this, but it's unnecessary to do this step.
Right.
Because it's a summation, and you can just keep adding things together. But for this, you have to specify the average as whatever you've ticked. So you do an average fixed on the dimensions
items.
that you have ticked, and then you're going to sum sales because that's what you're putting inside your average. So whatever you put inside, you put in the nested, and then you fix all of that to do an average. It's a bit complicated, but if you just enjoy the picture for a bit, you'll kind of just...
Can you talk us through that? So sum of sales.
Yeah. So the sum of sales is what you put inside your function.
Yeah.
So that's got to be identical. And the sum of sales is what's in the innermost nested LOD, right? Right.
Which is down to postal code.
So this is,
Order ID.
yeah, so order ID in this case. So
It's really because of the way averages work, because you have to count the number of rows as well.
Yeah.
So you actually probably could do this as fixed state and do a sum of sales and divide it by the count of the rows, and that might work as well.
Yeah, because that's all that's doing.
That might work. I don't know, to try it. But I think this is a good explanation, though, because basically you need to create a data set to the inner part, the blue part she has there, is really creating a table that you're then basing your average off of.
So yeah, it's because you're saying that you want to get this sum from these tick parts, and then you're actually calculating an average, then you have to do that on
Right.
whatever you've unticked.
On that table, right.
So
Yeah.
it's really quite cool when you break it down like that. I had fun building this and testing it to make sure it worked. So I'm glad to be able to share it.
That's good.
And sorry for taking up so much of your time, but it was a big topic, and Andy gave me a huge topic to do, and I enjoyed it, and I even missed out bits, but hey.
It's okay. Great explanations. Great job. That was meaty. All right. Whose computer are you guys presenting from?
Yeah, we'll do set up.
It's Alex's way of getting out of it.
Yeah, wait until you see my bit.
Is that it? This is your part?
Oh, that's me.
Oh, the two AJs.
Isn't it cute?
That's really cute.
Capital J, little j.
AJ scored.
Except Tableau reads them both as the same as they saw the other day.
Ellie's still with us.
All right, guys. Me and Alex, we're going to talk about order of operation with LODs. So first part of it is just going to be how order of operation works within Tableau, and second part is going to be with LODs. So before we start, can anyone answer that?
51.
51, yeah. 51. So just like how we learned it as kids, like how algebra works, you can't just do 9 times 10, 9 plus 10. You definitely can't do that. But you definitely can't do that.
Well, if you turn the plus sign 45
Literally.
degrees, then maybe.
Potentially start to play by the rules. Rebel. So yeah, so we all know how it all works. The law in like bid mass, bottom mass, where we're gonna go. So brackets or order.
You never had a bottom mass?
No.
Bid mass.
That's the order we go. So you do brackets, order, division, multiplication, addition, and subtraction. Very simple. Just know it. So just like in algebra we do it. Tableau kind of has a similar thing as well. So this is essentially how it works in terms of order of operation. So anything from calculation to filters, it just depends on how you order of operation works. I'm going to work through most of it until at least the LOD part, and then we're going to kind of expand on that. So like I said, the hierarchy shows the order in which like each of the operation or actions are carried out. So we're just going to go through it and then explain it a bit further. Well, we're going to refer back to that throughout the presentation. So one of the first things you need to learn when you use Tableau is granularity. So you need to understand where your data is, or at least what level of data you want to look at. So firstly, basic principle is the more granular the data you look at, the less aggregate it's going to be. Very basic. And two other things, and this is very important, especially for LODs, is the measure is what gets us the aggregation, but then the dimension is what specifies where the aggregation is happening. So, we're going to show you examples of both of this, and then it's going to be a lot more clearer than how we explain here. So just going back to the, not that one. There we go. It's a little laggy. Okay, so just going back to that table, we're just going to work through most of how it all, the filtering works. So if you look at the extract filter, is the most top level filter. This one's used if you want to if you have a big a data set and you just want to cut it down and make your everything much faster, is what you use this for. So for example, let's say you've got a data set full of different states, loads of data, but if you just want to focus on California and you're just going to be working with California, you can just take that out, make that into a TDE file, which is that's the main difference between this and data source filter, is you can make that into a TDE file and you can keep that as is. And then moving on to the data source filters, that's here you can filter out California or any other state that you actually want, but then it doesn't create a new TDE file. So all of that data is still there if you want to access it. So it's really useful if you want to control or govern how other users use that data set. So if you just want someone to just focus on one particular item of it, just give them access to that part of it. And then context filter, again, it's a third level filter. So anything, I'm sure we've used it throughout the week. So as soon as you add to context, it's one step higher than fixed LODs.
What's context?
So have you used let's go to...
You're supposed to be a team.
Yeah,
That's a good question.
yeah. So let's say I think it should work. Let's just put, I don't know if that's going to work, but...
Need region. Get region.
Yeah. So now I can apply city to context. So now that's the highest level. And that's higher than any of the if I put fixed LODs.
If you put another filter underneath that, it would do that city one first, and then the
Does
next
region?
Exactly.
It's region. I
Yeah.
don't know if it works these days.
So it's like Lee said, yeah. So that's essentially. Let me just go back to that one. Next slide. So so context filter comes up. So after this is all the stuff that we're going to talk about mostly is the LODs. So again, LODs are level of details. The two main things you do need to understand is include and exclude LODs are really dependent on what's in the view. So what's in the dimension filters. So you need to pay attention what's actually you're visualizing and then kind of work from that. Fixed, on the other hand, it doesn't matter what's in the dimension field, which is the main reason that it is much higher. So fixed is higher than include and exclude. That's quite important to understand as you go on further. Should I include and then show you an example, or how do you do it?
Yeah, well, I'll take over for a little bit. So, well, UJ mentioned, yesterday, basically, it just clicked for me, had a light bulb moment with LODs, and it was around understanding that those dimensions in view actually play a part. So, for example, do you want to knock up the screen with some dimensions? So, if we've got the two pills, so this is dimensions, and we've got measures. So AJ did touch on it. So weird saying
UJ?
Yeah, UJ, sorry. So measures, he touched on it earlier. Measures are affected by these dimensions. And equally dimensions, whatever you have in the view, will affect what you see in your measures. So, yeah, it's a good one. No, that's fine. So, when we look at this is showing, like Mina was saying earlier, about the aggregation. The sum of the profit here is being determined at a state level, which I think is really important. Obviously, people can shout at you as much as they want. But as soon as you understand that with LODs, it starts to click into place. Because, so for example, with this data set, we could look at, so what if we were to do an LOD around city level?
Can I make a new LOD?
Yeah, you could do it in this one even if you wanted. Right, why don't you show the map? The map's probably the easiest, isn't it? I think it's also good.
Just make it, you see that one.
Yeah. So obviously, this is, Ellie, do you understand this? You're probably the best person to talk to. So you know what a blue pill is, right?
Yeah.
Particularly nasty headline.
Yeah, when you've got. All right. Well, let's. So I think that's point one. Is understanding that dimensions play a big role and essentially tell you how to cut up whatever measure you have on screen. That for me was a big point. And then the next point was understanding how the data is put together. So if you just click on view data, that one there. So when you first see this data, obviously it's but you understand how it's kind of broken down into kind of different levels. So obviously you're first going to think, it's broken down by order ID, but it's not really. It's actually broken down by individual sales. So once you start to plot that, you see a kind of hierarchy coming out. So you see sales into an order. Obviously you could have many sales into that order. That order is then broken down in this data set into you've got cities above that. So you can have many orders into that city, then states, and then obviously up to country. We've only got one country here, so put many states into that. So once you start thinking about your data like that, you start thinking how you can cut it up differently. And so when you've got certain, so if you want to run through an example with an LOD, because LODs we use, for example, if we have certain dimensions, so here you can see we have country and state on screen.
Yeah.
But maybe we don't want to see just that. Maybe we want to see a city level, but keep that visualization.
I think the best example for that one would be, so right now,
Oh no!
Just like me.
I don't know if this will reach.
Is that right?
Is it plugged in?
We got it.
Oh.
I got it.
So so this is a really good example. So right now we're looking at average profit, and then average profit per state. That's what it looks like. And you might think, okay, that looks right, like average profit. But the problem right now is that because in our pills it says just profit. So what it's doing is for each lowest level of granularity, so it's our sales. So it's averaging out, it's per cell in state.
Which is, it's actually adding up all of the profit and dividing by the number of records.
So, yeah,
numbers.
Yeah.
All of it, because that's how
The number, it's basically doing a count on this.
Count on
that. It's an individual count.
But then if you want to look at that, but that's not exactly what we wanted to look at. So that's why we need to make an include LODs. And so if we want to look at a city level or state level, we're going to have include LODs. So if we look at this LOD here that we made earlier. So right now, if you want to look at a city level, then that's literally why you use that. Yeah, do you wanna...
Yeah. So obviously, before the LOD comes into the picture, we are sorry, bro. Before the LOD comes into the picture, AJ's right. So we've got state in view, but we're actually going right down to this kind of count of sales level, like the bottom level of aggregation that we have. So when he brings in his include, what this is telling it is, although city is not in view, I want to look at this level of aggregation, and instead of like looking down to sales, it's going to do a count on city if we're going to do an average, for example.
So yeah, so if we do that, then again we wrote this earlier. So yeah, so right now we've just put same information, but yeah, it's literally like LOD include LOD. That's what we used earlier. But again, like you can definitely tell the difference, obviously, from that to that.
So you use an include because you want to add detail to the
Detail.
So yeah, because we're going down this. So in terms of we are increasing the granularity, increasing the granularity, reducing the aggregation.
Right.
Because we're going down, we're going to use an include.
Right.
Equally, we could use a fixed.
So it's showing you the average profit per city within state.
Exactly,
Right.
and that's the big. This is the big thing to get.
Yeah.
This is yeah. What it was, right? This is what it was. Yeah. Because without that include city, what it's saying is it's at state level, but it's still going down to the individual sale.
That's
okay.
It.
Then you put the include in. It says no, look at city, but leave it at city.
So
it's just
well done.
get a bit. You deserve it. You deserve it.
So yeah, so that would be include. Yeah, that's include. This is low granularity. And now let's look.
We're on a roll.
Exclude.
We're on a roll.
Yeah, should we do this?
Yeah, let's do it.
So right now.
Right, what have we got? So okay, so now we're down to right. So let's try rub this up.
Really city level.
So now we are at the city level, but we're still looking down at this level because we haven't specified an LOD. So it's at the city level, but we're still looking down to the bottom level of sales if we were to sum or average. It will do a count on the number of sales within that. But then UJ's going to smash up.
Yeah, so right now, like the viz is also showing like the sum of profit in the level of each of the cities.
Yep.
But then, what if I want to keep this viz, but then I kind of want to know the sales of state level sale or something like that?
So you want to basically show where you've had sales.
Where I've had sales, which city I'm actually operating in. But then
every city and every state to have the same.
To show the same for that
state level.
Yeah,
state
you want
level.
to see your state level, but you want to see which cities are in there.
Right.
Like are operating within those states.
So that's when exclude comes in very handy. So again, so if you like exclude it,
because we want to keep city in the view, but we want to roll the data up a level.
Right.
So again, like I said earlier, it's really important when you use the include and exclude to know what's in the view and what's in the dimension field. You have to keep that in mind all the time.
So this is now saying.
Sorry.
So if you go open up your include,
Sorry,
open up your include again.
That's the exclude one.
This is exclude.
Yeah. Open up your include. And if you're going to put that into just one of them, would be good.
Yeah, we'll do.
So this is basically because it's include. Again, you can replace the word include with for each.
Yep.
But you have to add the other dimensions into your sentence. So this is saying for each city, state, and city. Or I'm sorry, for each country, state, and city.
Yeah.
Return the sum of profits.
Yeah.
I think that's almost overcomplicated.
Yeah.
So this is where I was probably going wrong.
Yeah.
And like Andy, you know your stuff. Not going to hold that against you, but yeah, it was.
But basically,
So how would you put that?
I
into a
would
sentence?
literally be like, so I'm looking at that, and before we had the LOD, it was coming back down to this level. Whatever we had in view, yeah, it was looking
Lowest
at that,
level.
but it was coming down to this lowest level. With this, I know immediately it's looking at C, and that's where it stops. It's going to do a count of C. That's it. It would never go lower than that because I've got include.
It is lower than that. It's city and state.
No, but that's not low. It is the lowest because you've obviously got state above it.
No, because if you don't have state in the view.
No, but again, we've used that example in the state view.
We've used this one because we left state in the view.
So, yeah.
No, smart.
Yeah, he's trying to trip you there. Go forward for it, mate.
Okay.
Trying to trip you up.
You know stuff.
I know you're new to LODs, Andy. It's all right. You'll get there. You'll get there.
We'll get there.
So yeah, so now AJ's dragged it on.
Yes. so now we've got LOD, exclude LODs in the view. So if we hover around, so we can see every city that we do business in, that we have, we sold any products in. But if you hover in, it all tells us the state profit. So can you see how it can be useful if you want a certain type of view, but I want to add additional data to it?
Yeah. Andy shows a good one. So if you start a new tab, chuck on state.
So you said I didn't know what I was doing.
No, we had a lucky guess earlier.
Honestly.
And then so we've got some. What was it we were doing? We wanted to know the percentage of sales. Was it percentage of sales within each state? Yeah. Okay. So we're going to need some of sales.
Should put that
the city on there as well. Right?
Yeah.
City is
Put Chuck City on.
What do you want?
Right, so what we want to let's put it out to the crowd, see if you've been paying attention. So Ellie. So right, we've got a lot of cities in each state. So what would we use if we've got a city view? So we're obviously going to need, there's two parts to this equation, isn't there? So let's leave this because that's quite handy to think. But it's two parts. So we need to know over the number of stores in each number of sales in each state.
So you want city sales divided by state sales.
Bingo. So city sales over number of sales in each state.
Or amount.
Yeah, whatever.
Some sales.
Yeah, it's some sales, same as.
Some sales.
Right. So so Lee, look at that. So we've got city in view.
Oh, right,
so
so
we've
you
got
don't
city
need
in
to
view.
fix it.
Yes, city in view.
Yeah, that's fine.
Well, right, okay, so we've got two different levels, haven't we here? State level.
Yeah.
This is a state level.
So the LOD needs to only be at the bottom.
So if we roll up, what do we do?
Include. Exclude.
Exclude.
Yeah.
Second guess.
Granularity.
You had 3 lights, you smashed it on the second. So no, that's it though. That's it. And you see why? Because we've already got city in there. So we don't need that.
Yes, you can do it with an LOD, but I would argue you don't need to because the dimensions are already in the view.
Well, you went asked. So that's fine.
But that's what we learned from the table. That's what we learned from the table counts.
But no, that's really good. And do you understand why? You understand why we need that next level? No, city.
Exclude the city.
Because otherwise it's going to calculate at this level, which would be wrong. We need to calculate at that level.
I'm with you.
Okay, so what would you say? Okay, so you're halfway there. So we've got exclude because we're looking at. So right, exclude what? Not you.
So we exclude city.
Bingo. Right, AJ, you're writing this in.
So exclude.
Exclude city.
By some sales.
Bingo.
Else.
Yeah, none of that.
Else.
No, that's fine. So that's on the bottom. And then city sales is obviously we're at city level already.
So you can just do some sales.
Cracking. Good lad. Sum of sales on the top. Can AJ manage that?
I don't even know what it is. What was it?
So sum of sales.
There's two.
Yeah, sum of sales divided by exclude. There you go. Make sure that sales is
All right, we get the idea. Move on.
No, we want to see Lee get it right. Then colon.
Just put that now.
No, that's fine. No.
Then colon, sum of sales,
Bingo.
and then squiggly mustachio thing.
Curly braces.
And then
Marcus, you're on the verge of getting sacked. Call them braces. Curly braces. You have to put some around that.
Some around that, because we need to aggregate it.
No, around the LOD.
They're down around.
Around the exclude. Cheers. Well done, Ellie. Cheers for including. Yeah, there you go. Then chuck it on the
Apparently
other.
my talk wasn't taken in very well.
You gotta do some of the sales at the top as well. You got rid of your sum of
It's
sales.
just simple, really, isn't it?
So intuitive.
So intuitive. Basically, just aggregate everything.
Yeah.
If in doubt, aggregate. And then smash that out to colour. Oh! And then
Let's ask him. Like, you know what we're
Small
So,
audience
what do you reckon is happening right now then?
So what's that showing?
What you just said.
Sure. I mean, I can't see the sketch.
So yeah, these dots are essentially, so this is the percentage now.
So at the city level, we're showing this.
Why don't you hover over
Yeah,
those?
almost there.
Percentage of the state that is contributed.
Pretty much, yeah. So
Nice.
out in
Wait, very clear
What
sentence.
if you go into Vermont,
At the state level, the individual contribution of each
All right,
city.
keep going. We got more presentations to get through here.
Just quickly through the smash the fixed
right?
one.
So we're like through the first part. So now we go. Now, well, we hope that's useful. Like those are my two top. AJ did a cracking job.
Yeah, the fixed one is, I don't know. So yeah, so fixed one is essentially, like we said, like it doesn't look at the dimension. So right now, in behind this, like obviously we're in the state, we're looking at a state view. Sorry, yeah. So we're obviously looking at a state view, but then if we wanted to look at a city view, or even like lower than that, even if we want to go granular, we could do that with the fixed LODs. You're gonna draw pictures out?
Yeah.
So essentially, it's a very good way. So, but one of the big tips that we learned is if you want to do it, then make sure you have the string. Like, so you don't just put city. Like, you could potentially do like fixed and city, but if there's multiple cities, then you're gonna get like all the values are gonna aggregate towards that.
It's the same city.
Exists
more than
different-
one
state.
Yeah, more than one state. So it's much better to do as cities. But even if best practice would be to even write the country as well. So if you do have multiple countries with similar city, like neighbor
Every
cities,
day.
Always practice LOD caution.
yeah. So yeah, do you guys have any questions?
Yeah, any questions?
Yeah.
One happy customer.
Yeah.
Oh, covered all of my questions.
We're here all night, guys.
Hurry up, everyone.
You don't choice, wait.
Who's next?
Marcus.
Marcus.
Don't have time for this. Go, go, go.
No toilet breaks.
If anything, it helped me.
Yeah, to get some. We got
I
it.
think she talked fast. Come on, Marcus.
It's so much easier when you look at it. When you
Yeah,
know
it's
all the
true. Yeah,
levels.
especially having them in the view, like stacks, it really helps. I think, like having them on marks card like that. Thanks, man.
No,
I owe you one. Facing your demons, Marcus. Facing your demons, Marcus.
I'm actually consulting.
All right, guys.
Hello everyone, my name is Marcus, and today I'm going to be talking to you about how to build a percent of total area chart with filters. So what I mean by this is we're going to build a total area chart, build a percent of total area chart, which when you filter down to a certain disease, the percent of total for that disease remains the same.
It retains the percent of total.
Yeah, it retains its percent of the total and its shape within the area chart. Okay. So during the week, we were sort of given a challenge to answer this question or this scenario, which is for each age group, what percentage of illness does each disease account for? And when you filter down to a specific disease, like I said before, it keeps its percentage of total. So yeah, as we can see in this view here, what we have is the area chart. We've got our color code on the right, and we've got our diseases our disease filter in the top right corner. Before I go into that, I do want to show you sort of the kind of data that we're going to be working with. So if we have a quick look at the data source. So in here you can see we've got the numbers. We've got the age, we've got the disease, we've got the disease copy, which I need to take up. Well, the ones we're going to be focusing on using are age, disease, patient, and patient count. Okay. Those are the main three that we're going to be using in order to build this visualization, and also to filter out using an LOD. So yeah, so I'm going to show you how I sort of got around to doing this. So before I actually jump in and show you how to build it, I want to show you the quick way that I sort of got into building it. So thinking about how I'm going to put it together, what goes where, how it's going to look before I actually try and visualize it. So a good tip Andy taught this week was to sort of use a a tabular view to build what you want to see. So for example, we're going to pull in the age into columns. We're going to pull in the disease onto
rows.
Yes, into rows. We also want to filter this as well. So when we do our percent of total filter, you'll be able to see what happens before we add the LOD and after we add the LOD. We also want to have in there as well the patient count. So right. So yeah, what we can see here is that across each column we have the age of the patient. So you can see you've got a patient who's age 1, 2, 3, 4, 5, 6, up to 72, I think it is. And in the rows we have the disease. In view, or in our table, you can see we've sort of got the patient count per age by disease. So top left, we can see that acid reflux. For patients, there were 1,405 cases reported for 1-year-olds for this disease. And yeah, what we want to do is sort of, as the question says, we want to find out what percentage of illness does each disease account for. So building onto this, initially when I first approached this, I tried using a table calculation. So we came into here, we chose percent of total, which immediately gives us all the wrong numbers because it's trying to calculate it all by table across. And this is quite a wide table, so you can see all the numbers. However, what we actually want to do is compute using table down. So now we can sort of see for 1-year-olds, acid reflux accounts to 48.2% of reported cases in that age group, and asthma 41.29. But the issue is, if we were to filter down to a specific disease, acid reflux doesn't actually account to 100% of cases across all age groups, and all diseases. So what's happened here is that Tableau sort of looked at it on a row level and just brought back the actual percentage for that. So as we can see here, we've got 100%, which is incorrect because it's been filtered down, but it hasn't taken into account that there are more diseases within that age group.
So this goes back to the order of operations. So Tableau is running the dimension filter before it's running the table calc.
Yeah.
Right.
Yeah. So in order to get around this, after a lot of head banging, a lot of tears, a lot of crying, we came up with a sort of, I found an LOD that we can use to sort of give us the right number that we want to use for this. And for this one, I'll call this the correct percentage of total. And what we want to do for this one, so first of all, we want to calculate the percentage of total. So we've got the, first thing we want to do is get the sum of the patient count. So if you can remember from before, the patient count is the number of time that illness has been recorded for that age group. So what we want to do is we want to sum that all up and then divide by the sum of, however, we need to use an LOD here to fix it at age, so that once we do our filter, it will still return back the percentage of that disease within the age group. So if you remember back, so as you can see here, we've got acid reflux at 48.27%. So when we filter down to acid reflux, we want that number to remain the same for 1-year-olds. For 1-year-olds and each age across that disease. So in here, we're going to use a fixed LOD. And what we're basically saying is, for every age in here, return the sum of patient count. Yeah.
I think your mustachio needs to go in between.
There we go. Curly bracelet needs to go in there.
Team curly braces.
So yeah, so we've got our fixed LOD inside of an aggregation calculation. So what we're saying here is, for each age, return the sum of patient counts, but then sum up again, well, give us the sum of that. And then, yeah, so we're going to divide the patient count by the sum of that fixed LOD. Right. So if I click OK. So now what we're going to do is,
so we know it should be 48.27 for acid reflux, right?
Yeah.
Okay.
But before I drag it into view, it's a good practice to make sure you change the number format because it's going to be a percentage. So if we change that to percentage straight away, when we drag it in and drop it over the old one, you see nothing's changed.
Boom.
And now hopefully when we go into filter down, so if you remember for age 1 acid reflux 48.27%.
Yeah.
Let's have a look.
Fingers crossed.
Boom. You remains at 48.2%.
That's it, done.
So then how do we turn that into the chart?
So, right, going back to our chart now. Right. So, we're going to need to build this out. I've kept the
Do
disease
it from
on.
the table.
Hmm?
Do it from the table.
I want to rebuild it. It's because disease isn't being filtered properly. Sorted properly. They've sorted it in a different way in this example here. So I'm going to take that example here.
For the sake of the sorting.
So, right.
Andy, comes from an NHS background.
If you drag in the age, right, what else do we need? Patient count. Yep. You can see we've got our view. Oh wait, whoops, wrong patient count. Actually, no. I'm going to show you what would happen if we done it that way, using Tableau, so you can get a visual way of seeing it as well. So again, we're going to change this to a percent of total, and just like the last one, it gave us the whole percentage for everything within that. So within what's in our view, and then we want to compute using table down. So seeing that, you'll think, yes, this is right. This is what we want, because it sort of represents, well, it mimics what we can see here in the actual issue. However, once we go in and try to filter down, acid reflux for 20-year-olds, 100%, not right. So if we go back, and again, just to remind you of our LOD, or of our calculation with an LOD. So we can use this again and drag this over to replace it. So you can see it still looks exactly the same. However, once we go in and start to filter down, we can see the acid reflux at age 32, 16.44%, and it hasn't lost its shape. It hasn't tried to fill up the whole 100% because for that age group, it doesn't represent.
So Marcus, why did you use a fixed one? Why didn't you use an exclude? Change your calculation to an exclude.
Yeah.
So it's but we don't want to exclude age. We want to exclude disease, right?
Yep.
So that's essentially going to give us the same thing, right? So hit OK, and then filter it. And why does that break? Do you know? Do you remember why from the earlier presentation?
Because of the order of operations. So we're saying remove disease. No.
So when does an include or exclude filter happen in the order of operations?
After dimensions.
So because the reason the fixed works is because the fixed gets calculated before you filter.
Okay, yeah.
And include or exclude gets calculated after the filter, so after the dimension filter. So it's just, that's why you needed to use a fix there.
Yeah. And yeah, so that then is
fixed on age.
Oh, yeah. Right.
Oh, that does look fancy, but
quite cool though.
Sounds not odd like a troll.
Yeah. So yeah, that's sort of
All right.
how you build a percentage. Oh, I forgot to say it. Right. A percentage of a total of area chart, percentage of a total area chart with filters.
Very good. Well, and we should point out that you gave yourself this assignment this week.
No.
Actually, because you said you would explain it to Luke. Did you get it, Luke?
Very good.
Hey.
All right. I think we're done with Tableau. So we are, right? Are we?
Yeah.
Okay.
We are.
So we are moving on to, Rodrigo says, great job, Marcus. Thank you, Rodrigo.
Thanks, Rodrigo.
We're moving on to predictive analytics. Whose computer are you on?
Well, Lee's computer.
Yep.
So we've got Lee and Jamie presenting now.
We on?
Yeah, we're on.
There we go.
Me and Lee, we're going to go through predictive analytics with Alteryx. This is one of the most powerful tools in Alteryx. What used to take lines and lines and lines of codes in R is now simply used with 2 or 3 functions. Like you can literally plug some data into a regression and it can pull you out some predictions. Even though that's bad practice, we will now go through some theory behind different models and how they use and some different classifications, and then we'll run through a demonstration of a predictive analytical story that we tried to tell earlier today. So the first thing with...
Sorry, I'm in a weird screen where it's gone. It was in a weird presentation where I couldn't understand what was going on. Yeah, it's doing it again. Anyway, there we go. I've got it. No, see, it's doing it on my screen, but not on
Implementation mode, the data school thing might crash.
Just
It might be in
that's fine.
Is that fine?
No, it's not.
It's not. It's not syncing. So I'm moving it on here, but it's not on there.
Yeah,
But it's
plug
still
HDMI
Wi-Fi.
into.
Oh, is it because the HDMI is plugged in?
No, we need to plug it into.
No, you just be
just plug it in.
You have to be go to meeting.
It must,
Don't worry about it.
it must be plugged in.
Oh, what's it doing?
It's
But,
not.
but even on the screen,
It's not mirroring at all.
You present it as mirroring, right?
Oh,
no, not
Well, it's frozen.
my Google has crashed. My
Oh,
Google,
no.
Google Chrome has crashed.
Oh,
They just decided to move out of the way.
Yeah. Sorry, guys.
One second, he needs to rejoin the go-to meeting.
Wait, there's no risk that my Google Chrome will crash, right?
Will,
My-
you're up.
My entire presentation is on Google Chrome.
No, I think
That's
he
computer.
just has to rejoin the go-to meeting. So Lee, when you join back in, I'll just make you say you're offline.
Sorry. Sorry
After
about that.
break, drink break, everybody.
Okay, I'm back in.
Is it working?
But it's gone very strange. I'm going to share. Okay?
Yeah.
Yes, sorry about that. And now if I go into slideshow,
First week.
it doesn't,
That's what it was.
it doesn't like it.
It got crashed again.
If I cycle through though, let's go back.
Yeah, we'll just cycle through.
It's not even moving.
No, it doesn't. It doesn't move.
Click escape if you're in presentation.
If I do that,
You changed it down to...
Are you in
it's
presentation?
crashed again.
Can we, have you got it on any other computers? Or?
My Chrome.
No, but just do it and don't go into full screen. Don't go
Do
into
you want to just
presentation
drag it
mode.
into the,
Just don't go into presentation mode.
Maybe does he need to pull that out?
Come off
Yeah.
Airtable.
No, I don't think it's Airtable. Just do it again. But just don't go into presentation mode. Just leave it as is. And then just click
Yeah. But, okay, so I need to be made presenter again.
No, don't start.
I don't know how to make someone a presenter.
Yeah, exactly.
just right click
Have a bit of this.
and then make presenter. There you go.
Yes.
You can switch to
Okay,
Right,
so
we should be back on.
I'm sharing.
Don't go to presentation.
Okay,
Yeah,
so
presentation.
that's working. Okay, we'll stay like this then. So, second slide. Sorry about that.
Okay, with predictive analytics, there's 2 distinct fields. These are supervised and unsupervised. The best way to think of supervised is that the user has a distinguished dependent and independent variables.
this basically means that a dependent variable will be what we're trying to predict. This could be continuous or this could be discrete. So below here you can see I've got used cell car price and I've got, so someone will have a heart attack before n age. These are two different types. The top one's continuous because the sell price can be any amount. While saying someone has a heart attack before a certain age, that's either a yes or no, that's binary. And so, and the independent variables, these are the things used to predict the dependent. So for example, with the used car sell price, it could be model, it could be age, it could be brake horsepower, it could be mileage, it could be the amount produced. While if someone has a heart attack, it could be their age, it could be their sex, it could be their weight, it could be their fat intake, it could be their calorie intake. Basically supervised is, you know you want these independents to predict the dependent, so you're going to put them into a model to try and to gauge that relationship with the dependent and then use them to predict the dependent when you bring in a new data source that will include the dependent. Unsupervised, on the other hand, the model is basically trying to use a model to find structures and relationships between a set of variables. So for example, you can have a load of films and you've got no categories for them. And to find categories, you can put into data, for example, the ratings from critics, the genres, the box office numbers, etc. You can also do this with customer profiling. This is very relevant in marketing. So you could have for the customer, you could have total purchase values, last purchase, how active they are they profitable? And what an unsupervised model will do is you will put in all this customer information and it will try and group the customers according to some variables and then try and create distinct groups. Can we go? Now moving on, I'm going to go through now forms of supervised models, and the first one, this is split into two groups. This is regression and classification. To generally distinguish regression and classification, you would say you would look to quantify a relationship between a target and its variables with the least possible error. This is what I briefly went over earlier with the dependent and independent. The difference between regression and classification is this, which a regression is used to predict a continuous target, such as cells as earlier, using target variables. For example, I can say I have a 1975 Ford Mustang with 350 brake horsepower that's had 10,000 miles and there's only 5 in production. Can you predict what the cell value is? While with classification, you're looking to predict discrete classifications. This could either be binary, which is one I explained earlier. Will I have a heart attack or will I not before the age of 40? Or it could be distinct groups. So it could be, is the sales of this product very profitable, not very profitable, or unprofitable? For example, the example I've given here is related to the heart attack. Once it says, I'm male, 25 years old, and smoke 10 cigarettes a day.
So it says, my name is Lee, I'm 25 years old.
Sorry, it's not
Sorry, it should say, will I have a heart attack before I'm age 40?
Actually 23.
So that would be yes or no. I'm going to now move on to describe regression. This is generally like two ways that regression could look like. On the left is the Y column. This is what you're trying to predict, and underneath is the X-axis, and this is the dependent what you're using to predict that. And what regression tries to do is build the best fit line to match the data it's trying to predict. So here, this will be all the dots will be the students, and this is trying to draw a line of best fit to predict from a student's high school GPA what their university GPA will be. On the right, as you can see, this is a bit more curved and it looks a bit more complicated, but this is the line best fit, and what this is using a woman's age to predict how many births she will. Most people will define this as a difference between linear and non-linear regression, but in the most part that's true, but I'm now going to go through why that's not actually true in theory. So here, so as I said just now, regression is either linear or non-linear. The way to distinguish that is by the linear regression equation, which is this basic formula below. So what I'm going to do now is I'm going to draw out a Y and an X-axis, as I explained what both are earlier. And the first part, the A, is the intercept, known as the constant, and what that shows is where the line of best fit will go through the Y-axis. And then what the B before the X is, this is the slope of the graph, so the higher it is, the more the dependent affects the Y-axis. or affects how much the y-axis rises as you go along the dependent. Also, what must be noted here is it can get with more this is just for one variable, which is why I've put b1, x1 at the end. As more variables are added, the calculation does get longer, and it would have plus b2, x2, plus b3, x3. And what happens there is the b will act as the weighting for the each variable as it's added along to the calculation. Yep. So yeah, next one then. Now, what's important with a regression is to see how well it works. Is you're looking to calculate the error in its predictions. So as you can see on the screen here, you can see the line here. Here's what it's trying to predict, and you can see how far away from you are from the line, and some are above the line and some below the line. So I've put here RMSE, and what that means is root mean square error.
What are each of the points?
So each
individual fields.
So for example, when it was trying to predict a student's GPA, each individual point will be the student, and the bottom bit will be the high school GPA, and the left will be the university GPA. And then, as you said, like the error here is the distance from the line. But if it's underneath the line, it will be minus, while if it's above the line, it will be positive. If we just sum them, it could end up being close to 0 or minus, because...
So does it try to put half above and half below?
Yes, I explained that earlier. When a line, because the line will try and give the best fit, and then from the best fit to predict if the best fit's wrong, you will sum the difference. Each point is away from the line, but you need to make sure that by squaring the difference, it prevents this from being a negative or from being a low value when in fact it should be a high value.
Is there like a range that should fall?
No, because you can have, for example, you could have 1,000 students, or you could have 3 students. If it's 3 students, it's not going to be that high the error. But if there's 1,000 students, it could be a few thousand. That makes sense.
So when you say you calculate the RMSE, what are you looking for?
That's
you mean basically it's good or bad?
Yeah, like why calculate otherwise?
Because I'll use this to calculate when you're comparing it to other regression models. This is what this is for, and this is to predict what the best regression model is.
So no matter the model you use, you want to calculate the RMSE, so you know which one.
Which one has the least error? So what you'll see when me and Lee, we don't do RMSE, we do a different form. We see which predicts the most correct, because we're doing binary classes, classification classes. It's not binary, it's classification where it's distinct groups. So we're predicting whether it picks that group correct. While here, you're just seeing how many different individual aspects is predicted correctly, and then what you'll do is you'll use 3 or 4 different regressions, and then sum the root mean square error between 3 different regressions, and then from that, whichever one has the lowest error will be the best predicting line, and then you'll move on forward from that using that as your predictor. So that's me trying to give a brief overview of regression. I know I've missed a lot. I've missed a lot here.
Like the reason it's better with the lower error is if the shape is wrong, it will have a big error, because the line tries to minimize it for whatever shape it is. So if it's linear and it tries to draw a straight line for whatever you put y and x.
Well, if it's curved, you still want to discount the ones that are above the curve.
Yeah,
it will try. So the curve will still try and minimize the error, so that the shape is slightly different.
Right.
And it's just whichever one of those is better at minimizing the distance between by the shape of whatever your relationship is.
Also, so next on me and Lee, we're going to go through classification as I've described classification. This is when you have the y-axis is not continuous, it's discrete. So, for example, for logistic regression, you'll have a binary y-axis. So that would be just one or no answer. So the one we did in class the other day is would you survive the Titanic? And then you'd use variables to predict that y-axis, such as age, ticket you bought, class that you stayed in, and so on. And logistic regression mainly deals with that, so we won't be going for logistic regression when we do our calculation. And the way logistic regression works is, if the prediction is above 50%, you will do it as a 1 on the binary code, so the yes, they would survive. Or if it's below 50%, obviously it's no. Well, the way we're doing it...
Ours is on a scale of 1 to 5.
Ours is on scales of 1 to 5, so we're going to do a classification for a group of classes, which is how much alcohol students drink in the week. We're going to try and predict that, and I'm going to pass on to Lee.
School students or?
Oh no, we found a data set on Kaggle, and we found one data set that was university students taking a mathematics course, and another one was students taking a Portuguese course. So we're going to run some models through the mathematics course find out what the best model is, and then try and predict how much drinking the Portuguese students will drink. So this is what Lee's going to introduce now.
Hi, yeah, my name's Lee. So before I take you to the workflow itself, we'll just go through this model to just an overview of what we're actually trying to achieve in Alteryx. So we're taking a data set to train the model. So we're going to go through a few different types of models and test to see which model is the best. And then after having done that, we'll take that best model and run the calculations that it has made through a different data set and check that it actually is good at predicting what we've asked it to. Okay, so let's take you to the workflow. Be gentle. It's the first one I've kind of built on my own. So, all right, so let's first start by looking at the actual data. So we have a set of data from maths students, demographic data, their age, stuff like parental status, the travel times of their course, all of this kind of stuff. Let me just hide this. But what we're actually interested in is this field called DALC. In English, that means the weekday alcohol consumption. So that's what we're going to try and predict.
So daily alcohol consumption?
Well, not quite.
It's not, 'cause it's on a scale of 1 to 5.
Because the one next to it is WALC, which is weekend alcohol consumption. Yeah. So the first thing that's really important to do is make sure you clean your data and select only relevant fields. So this is the part where we've done that. Let me just drop this down a little bit so you can see it a bit better. So this is where we're actually cleaning and selecting it. But before we select it, we can use a tool in Alteryx here called the association analysis. And running the fields through this, it actually calculates which ones have the highest association. So if I show you the output from that here, it brings you back a matrix. Did you want to talk about this a bit? Or?
Yeah, so what's important on the matrix, as you can see, it's color-coded. If it's red, that means there's a higher correlation. And as you see, this is pure red. This is because it's the same field.
I wish it wouldn't color in the diagrams.
Yeah. So along the bottom, you can see R1, which we're most interested in. And then as you move through.
As you move through, you can see which fields are more related. And as I said, usually a good correlation is above 0.7, thereabouts. But here, as you can see, we've not really got great correlation, but through going through here, Lee managed to pick out, how many fields did you pick out?
I basically picked out all of these ones that came up associated, really.
Yeah.
Apart from, obviously, the one of itself. That would be useful. So, having done that, we then selected these back here. I applied a filter to remove 0 absences because I thought zeros might skew the model. I wasn't quite sure. And then it was a point of actually standardizing them. So, you know, the ranges for these fields are on they're different ranges. Some of them were 1 to 5. Age was quite a larger range. And the number of absences, I think I saw up to about 52. So there's a lot of different scales. You needed to bring them down to the same sort of level so they had equal weighting. So this is basically what we did here through these summarizes and formulas. Following that, once the information was ready to go through, or the data, it was then about creating samples to go forward for the models.
Okay, yeah, the reason why here we have to create a sample, we need to split our original data set, because what we need to do is we need to use the estimation sample percent, which is we've chose 60, to run through the model, and by running through the model, it'll be able to create a regression equation, and then what we'll do is we use that regression equation to run through our validation 40% to see if it actually predicts well. Okay. And then from that, we will create a score for each model and then decide which model's best.
Yeah, so just to recap on the data that we have here, these are our chosen fields here. So these are the new standardized sort of values for each of the ones that we think are predictors for our weekday alcohol consumption. So now if we take a look at the models, so if I just expand that and bring this down a bit. Here we have 3 different types of models that we are relevant to this type of prediction. We have a forest model, a boosted model, and a decision tree. So these will predict in different ways, and I think Jamie, want
Yeah.
to talk about?
I'm going to quickly run through decision tree. I'm going to run by boosted because it's quite a complex and new regression that's used a lot, and it'll take a while to go through, and it's quite complex. While decision tree is quite easy to draw out, and I think most people understand it when you do it. And what a decision tree does is every single variable we've used to predict will ask a question. So, for example, it could be age, could be the first question, and then it'll group them. It'll say, if above 18, yes or no. Then this will divide our data into two distinct groups. Then after this, it'll ask the next question, which is, how many absences did they have? And it'll try and categorise this. It'll say like above 25 absences, below 25 absences. And it'll keep asking these questions and keep dividing our data through all our variables until it gets to the bottom level of the tree, where it will then add up. It'll create probabilities for each level of alcohol consumption due to all the factors that it's had yes or no for.
How do you decide the order that you put them in the tree?
I think it does it for us. That's one of the powers of using this thing. And what a forest model is multiple trees. So what it do, it have different orders of the questions, and I think that's why it's so powerful. Because why a decision tree will just have
So it's
one
like
order of
running
questions.
the decision tree multiple times.
Yeah, so that's why it's a forest. Yeah.
Oh, I see.
So if we go back
That's pretty
to
cool.
And that's why it's literally the darling of the
That's a good-
analytics world
that's
at
a
the
good
moment.
explanation for it.
Yeah.
So if we go back to how we configure these models in Alteryx, it's important to name them. And what you need to do is specify your target variable, which is our DALC here, and then also specify all the different variables that you want to go into it. And this is just repeated for all three of them. So following that, Alteryx, we will apply a score in Alteryx, which is scoring the potential or the percentage likelihood that it will fall in the category of 1 to 5. And all of those will add up to 100, so between the 1 and 5 value. Following that, what we've done next is asked Alteryx to bring back the score that had the highest percentage.
Because as we're doing classification, the one with the highest percentage can be the only answer. It's not on a scale, it won't be 2.5 with an error. There's only one answer you can have.
Yeah, and then we wanted to match it to the actual. So if it was the same, then bring back 1, which is yes. If it's not the same, then a 0. And just assign them their own equal field. We then summarized them so that we could tell how many it got right, and it just brought back a score
So wait,
for
can you
us.
tell me what that calc is doing?
what is that?
So it's
Just checking for all the scenarios.
Yeah, it's just literally checking all different scenarios.
all the data pin at the bottom up, so you
But what
can
are you
see
trying to
the
accomplish
output.
Oh
with
yeah,
this? Sorry?
sorry. So the
So
idea
this is
is
a
just to bring
classification
back.
problem, and what we've got now is we've got 5 columns
And then scroll a bit to
with
the
the
right.
different scores, and it has a percentage likelihood of each score. So what this calculation is working out, which one has the highest score
Yeah,
is going to be what our classification is going to be.
Yeah.
So we'll say, so this classification, so if 1 has the highest score, then it's classified 1. If 2 has the highest score, it'll be classified 2. If that makes sense.
And
And we
we're
need
aggregating the probability forest, the highest
Yeah.
probability forest against how
So
many
if you
got
view it
right.
on this top row, it's DALC equals 1, which is what we're aiming for, and go across to here. The percentage that was highest here was score 1, 96%, so it was right, which is what did we get it right? Right, 1, so that's correct. Does that make sense?
Does that make sense?
I'd say maybe the only kind of consideration is if you didn't want to have to hard code a lot of lines like that, maybe just transpose or something like that so that you have it,
Yeah.
and you could just
All
do
done
like
that
a
code.
Definitely.
Yeah, that makes that's definitely something to do forward. Yeah.
Yeah. You know.
Yeah, we're not saying it's the ideal way. Yeah.
Anyway, but what the key thing here is that it brought us back a result, so we could tell which one did best. We wanted the highest number that it got right. In this case, was the boosted with 75.
Cool.
So that is the model we want to take forward. So going on from there, if I just
Sorry, did I miss? What's the boosted one?
boosted is one of our models.
It's a complex new
It's
model.
really
That's
complicated.
yeah.
It's really new.
So it will often come up with the highest result in Alteryx because it's a very complex, and I think it uses multiple forms of regressions. And chooses the best one from there. I think that's what someone said, but don't quote me on that.
So what I'm now doing is taking boosted out, and I'm going to get rid of that because it's clutter. And we'll zoom back in because we're going to use it in our test. But we're going to apply a new data set to it. and we need to clean it first. And essentially, I've done the same thing as I did above here. I'm cleaning it up and standardizing it, ready to go into the new model, well, the chosen model. So yeah, essentially the same thing. One thing I didn't cover in the cleaning is that nulls. You need to get rid of nulls because models do not like nulls. So if any in your data, you need to get rid of them. So we program that into our new model and score it. And yeah, then what we've done following that is use a set of filtering and calculation to filter out the highest score, like the scores of 4 and 5, which are the highest alcohol consumption. So ones that fell into that category, and we labeled them as like a high risk. And from that, we've calculated students that are at a high risk of alcohol consumption.
Yeah, during a week when they should be
when they should be studying. We don't care about the weekend. You're allowed to.
You can binge drink all you want. Yeah.
What's the NWALC again?
So that's the weekend alcohol consumption.
So we use that as a predictor of weekday.
We did use that as a predictor.
It's a scale of 0 to 5 of how 1 to 5 of how much you drink. So 1's not drinking very much, or 5.
So why are these ones 5 to that? 1 for that. What's that?
Are they 5 for the first
Yeah,
column?
well, just because even though their weekend alcohol consumption is low, all the other predictors say that delta should be high.
It's not typical.
So
it's probably, as you said, this isn't realistic data. Probably we've got it off Kaggle. It's probably not going to be exactly students that.
the other predictors must be quite bad, so it's still predicting a really high delta, even though their weekend alcohol consumption is low. So it's just the aggregation of all these predictors through their model is saying that their delta will still be high.
So,
right, based on all the other factors. Again.
So this was us going through supervised learning. We're now going to move on to Will, who's going to go through the most, part of his presentation is going to have the most popular form of unsupervised learning, which is clustering. Which I'll...
Good job.
Well,
Your charger, the charger.
That's not mine. That's still me too. Actually, I thought it was mine too. I was like, if you see, I'll practice.
that's really
Yeah.
good.
You see the practice. Okay, so hello everyone, I'm Will. For anybody online, thank you for still being here after 2 hours of presentation. It's Friday night, so I'll try and keep mine short and effective. So Andy tasked me with presenting spatial analytics this week with Alteryx. So obviously we all know that Alteryx is an extremely powerful tool to get the most out of our spatial data. Everything from calculating the drive time between locations to finding the nearest store to a customer. So if you don't believe me, you can believe all these other companies on Alteryx's website that use it. And also you'll notice that I've actually built my entire presentation in Google Chrome. But so when we first got the assignments, Andy pretty much told me to just do a basic find the closest store to each customer. So I thought about it for about 45 seconds, and pretty much this is the only thought that I came back with. This is really, really boring. I mean, who really wants to spend a few hours just crunching this data, actually a few minutes in Alteryx, and figuring out what is the store that's closest to each customer, right? But then actually at a deeper level, I thought, do we even really care at a business level about what's the closest store? Like, isn't there something that's more important? And so my mind kept thinking and thinking, what is really the only thing that matters when it comes to business risk? And every idea I came back with, this is what my brain told me. Wrong, wrong, wrong. So I kept thinking and thinking, there has to be one. There has to be one source of risk that's just worse than all the other ones. And I know that you'll already know what that is, right? Until you say some suggestion to get it right, you're going to have to keep looking at Donald Trump's face. So can I get some suggestions? Something?
Likelihood to get hit by a meteor.
Oh, pretty close.
You know your-
Guessing based on random.
Andy really does know his stuff, doesn't he?
Asteroid. Oh.
Asteroids. Absolute impending doom. Nothing you can do about it. Millions of them just traveling around the Earth, all over the world. Nothing we can do about it. So obviously I thought the only real sort of location data I should look at is meteorites and how they relate to cities, right? So thankfully, there's actually a bunch of free publicly available data on meteorites on the internet. So this is a data set that I found in Kaggle, which shows meteorite landing data. So all meteorites over 45 kilometers that have struck the Earth. And then I actually also found a second data set, which has data on all cities around the world. It's actually pretty impressive. If you buy this, it's $200. You have data on 3.9 million cities around the world. But so just a huge data set about, just basic information about all large capitals, all large cities. And so I took the two of them together and I thought, well, what are my two assumptions when it comes to meteorites? First one, a meteorite never hits the same spot twice, right? We all know that. So if I know a city has meteorites that's falling really close by, it's probably a safe city to build a factory in. And second of all, if a lot of meteorites keep falling at the same spot, then I know it's probably a dangerous spot. So I probably shouldn't build factories there either. So going to Alteryx now, what does this look like? So at first, just basic, here's what my data looks like. So this is just my meteorite data.
These are just CSVs you had to download?
Yeah, just pretty much I had no prep to do. It was really, really clean data. But so what this shows is just the name of the asteroid, which is pretty funny, or the name at least of, so the name is usually the place where it landed. And then just a few other random fields, maths, which will come useful later, and then the lat and the longs, which is really the thing we're the most interested in. And the second of all, my city data, so also very clean. So it's the name of the city, lat longs again, population, country, and a few other fields. So the amazing thing about Alteryx is that really you don't have that much to do when it comes to spatial to at least create the objects you're going to need for your analysis. You can just use a create point tool, feed it your long and your lats, and it'll automatically build an object that looks like this, called a centroid, spatial object. And then if you look into a browse, so the map here isn't that beautiful, and I also just have so many things on the map that it's not really giving you that much information for now. But pretty much
that's every location where a meteorite has hit the Earth?
Hit the Earth, pretty much.
Oh, that's pretty cool.
So that's, every place that and we've actually got Antarctica on the map, which we almost never see, so I also thought it was pretty cool. And then I did the same thing for cities. So just built a map which has 3,000 or so of the largest cities and capitals around the world represented. So first we're going to go with my first assumption. A meteorite never hits the same spot twice. So let's find the cities that have meteorite craters that are extremely close to them. So to do that, I'm just going to use a distance tool. Again, very simple. You just plug in your two, what are they called again? Just spatial points. And then just link them together, and Alteryx will immediately just give you an output that has the, like this. We'll create two columns, one which actually tells you which one of the objects is the closest one, so to your city, sort of the one of interest, and then the distance between that object and your, universe centroid. So after that, I just had to do a little bit of cleaning, changing some data types, removing all the fields I wasn't interested in, then sorting them to make it as clear as possible. Sort is also a really easy way to see that I've probably got some broken data in there, because I'm pretty sure that Russia is not in Northwest Africa and in Allen Hills and all these places at the same time. So just nice and easy way to identify outliers or broken data. So instead of actually fixing it, I just removed it. And then just filtering the big cities, because at the end we are only interested in opening our factories in big cities, right? So just using a quick filter to only keep the cities at a population over 100,000, and we are left with this, which is still an ugly map. But at the same time, I thought I could probably get a lot more out of this, right? I mean, Alteryx is a really powerful tool. Now all I know is that if I want to open a factory, I should probably go to Stavropol in Russia. It might be a little bit, cold, but based on my assumption that meteorites never hit the same spot twice, I'm pretty safe there, right? I'm also pretty safe in Pittsburgh. We could tell GM they're also really safe. I mean, no meteorites coming in soon. But I thought, let's get a little bit more of this. So I thought, let's build a sort of danger zone around each city. So sort of a radius or sort of circle around each city, and then find how many meteorites have fallen within that area. Okay. So a cool tool that Alteryx has for this, which is also very simple to use, is a trade area. So I've decided to build a trade area around each city with a 20-mile radius. Blast radius. There we go. And so what this will do is just build it's called a radii polygon, which is also known as a circle around each city. Around each city. And after that, because I've already built my spatial point for each of my meteorite craters, I can just use a spatial match, and it'll automatically tell me which are my cities that have meteorites that have fallen around them, and just place them on the map directly. So now the visualization gets a bit more interesting. I find actually the Alteryx map to be a little difficult to play around with, especially when you have just thousands of things in the view. But I think it's worth at least showing just how easy it is to build something like this. And if we just zoom in a bit into Europe, there's some interesting stuff. Okay. So you can see a trade area around all the pretty much major cities of the world and all the craters that fall within them. So if you live in Bern, Switzerland, I would say move the hell out because that is a danger zone. But so here's our first map. But then I thought we'd still probably get some more stuff out of this, I mean, Alteryx really expensive, right? You might as well use it.
They sell like meteorite insurance for homes, or
the what?
meteorite insurance.
Yeah, exactly. I started a business, right? The info lab should stand. So once again, I filtered out this broken Russian city, and then I used the summarize tool to be able to sort of count the number of meteorite craters that fell within each trade area.
Aberdeen, USA.
Yeah, so there's probably like 20 Aberdeens in the US. And then I summarize all this data.
North Dakota, I think.
And so the one thing that's kind of annoying with the summarize tool is I lose some of the finesse of my data. So if I want to be able to count the number of craters per sort of blast radius, I'm going to have to average out all the masses of each of the craters, the population for the cities as they evolve through time. But for the interest of this presentation, I just left it that way. And as you can see, I count by the ID, so each asteroid is identified by unique ID. So I'm just going to count the number of IDs that fall within that. And I get something that looks like, well, actually, let's not look at it just yet. So this is when you get to the part about unsupervised learning, right? So I could myself try and figure out, which are the cities that are the most at risk of being destroyed by an asteroid, or I could just let Alteryx do it by itself. And that's where unsupervised learning comes from. The reason it's unsupervised, if you remember what Jamie told you, is that if you have a supervised learning set, you pretty much have data on what your car price is, and then all the factors that impact it. You actually know what that car price is. In my case, unfortunately, there's no database about which cities were destroyed by meteorites. So I can't actually try and predict it on my just different variables. So instead, I have to ask this statistics to sort of look for patterns by itself. I can't regress the mass and the number of meteorites that have hit near that city on the number of cities that were destroyed. Instead, I have to tell it, just look through this data and identify patterns by yourself. So that's where k-means clustering comes in. So I know it sounds a bit complicated, but it's actually really not. And instead of taking the time to explain it, I'm going to show you a video of how it's done. And hopefully this video won't.
We'll have to show videos.
But so pretty much, I'm actually going to explain it for yourself. So what k-means does, so when you get to your menu option, what it'll ask you is how many centroids do you want to start with? It sounds really complicated, but all that is how many of these triangles do you want to start with? And what it's going to do is, so it's going to start by placing them absolutely randomly. So these are all your data points. And what it's going to do is calculate the distance between all these points in these circles. And if the point is closer to that circle, it's going to assign it to that cluster. So hopefully the Professor Mason's video speeds up. So
I think it's playing.
I don't think it started.
I have it, I think.
Oh, that's
Yeah, it is.
Oh, yeah.
Okay. So because we're doing Euclidean distances, so it's a math thing, but pretty much you know that all the points that are to the left of this line will belong to that triangle,
right.
and all the points to the right of this line will belong to this yellow triangle.
Just kind of finding the nearest.
Exactly.
Yeah.
And then what it does is that it averages out the distance, all these distances, and will sort of calculate the center of gravity, and it'll move that centroid to that center of gravity. So it takes all distances, averages them out, moves the triangle, and it'll move this little triangle to the new center of mass. Everybody understand the center of mass concept? So that's what it does. So it moves it to the new center of mass. Come on, do it.
Kind of adds up the x and the y for those points and then takes the average.
Exactly. That's exactly what it does. It's really not a complicated process, like at all, like mathematically. And so then it redraws a new triangle, but now it's going to redo that first step. So it's going to calculate the distance between all the points and that centroid. It's going to reassign them to that new cluster. And
keep going through that
exactly,
process.
so it's going to redo the distance, recalculate the center of mass, and it's pretty much going to keep doing that until it can't do it anymore, until all the points have been perfectly assigned between each cluster, and if it recalculates center of gravity, none of the points change. So here, as you saw, these points were yellow, now they're red, and so it'll keep doing it. So now it's going to move this one here, move that one there, and it's pretty much going to do. So that's just k-means clustering. It sounds quite complicated, but actually all it does is draw a random
That's a
point
good explanation.
and associate them. So that's clear. Just skip on now. So to do this in Alteryx, it's also not complicated.
So I guess
at all.
in theory, every time the triangle moves, it moves less and less.
Yeah, exactly. Yeah. Or it could, but all that matters is that the computer will do it ridiculously quick. So it doesn't really even matter how much data you have, but it'll just keep doing this over and over
That's
again.
what Tableau does too.
Exactly.
The bootstrap replicates, I think, is actually the number of times it does that. I think I checked this morning.
Yeah, it could be. So that
Bootstrap replicates.
Oh, okay.
I was watching a video this morning. I think that's good.
That's what bootstrap
So you can
is.
tell, so you can tell the maximum number of times to try it.
So you keep doing that, yeah.
Okay. Oh, cool.
And yeah, so the cool thing as well about Tableau is that here it's quite simple. I mean, from Alteryx, from just looking at my data, I kind of have an idea of the number of clusters I want to build, but sometimes you just don't. You have too many variables. It's quite complicated. So it comes with this pre-built K-centroids diagnostic tool, and that will pretty much give you suggestions on the number of clusters and things you should build. So all you have to do is just connect your data to it, tell it which fields you're going to want to build your clusters on. So I'm just going to do it on the count of meteorites around each city and the average mass of that city. Then you want to standardize them for the same reason that Lee said before. All of them have different dimensions, and pretty much you standardize them to make sure that they all capture the same amount of variance within your data. Let's just leave it there. That's a good enough explanation, I think. Clustering method will usually do k-means, and then here you do the minimum number of clusters you want, the maximum number you'd want. Bootstrap, I think you're right, is the maximum number of runs it'll do. And this bottom thing is actually, I'm pretty sure, but it's just cool to know. Number of starting seeds is just, it places them randomly, right? But randomness doesn't really exist. It's a pseudo-random process. So it kind of mathematically builds this randomness thing. And as long as you and your friend select that same number, it'll put them in the same spot. So that's just a cool, so as long as if you selected 50 and your friend did 50, randomly it would assign put the centroids in the same spot when you start. So that's just a little geeky statistics thing. But so the output from this is what you're interested in. So you're going to look at this, which is incomprehensible. What you're mainly going to look at is these two graphs. What these two graphs are, just briefly, what you really want is to pick the number of clusters that has the highest mean. So the top one tells you how similar sort of the units within your cluster are. So mine would be how similar the meteorites are. So how many times, so like the sort of frequency of when they hit around a centroid and their mass. And the bottom one tells you how different each of your clusters are and how compact. So it's sort of, you want to have a really small island and all these islands to be really similar, but really far apart from one another. So you want both of these things to be as high as possible. So as you can see in mine, in all my clusters, the clusters are really similar to one another, as you can see from this mean being really high. And the box plot is quite small, so all the clusters are pretty similar. But here you can see that the mean is really, really low, so that means that my between cluster variation is pretty bad. So in this case, all you would do is pick an average of 1, so I'm going to pick 3. So I'm going to build 3 clusters. If this makes sense or doesn't make sense, you can ask questions.
Like the island analogy.
I know you do. I think that's your analogy. And pretty much all this is going to do is, so after I run my data through it, it's just going to assign each of my rows a cluster based on the field that I told it, which was average mass of all the asteroid hits and the total number of asteroids. Good thing to know, at first when I tried to do this, I still had my geographic fields in it, and it wouldn't do it. It wouldn't do the k-means, so I actually had to remove it. So it's good to know that if you try and run a k-means clustering, but you have a geographic field inside, it'll break.
So is that your centroid that was in there still?
Exactly, yeah. So what I did,
swipe that out.
just removed it, and then I joined them back up so that I still do it. Yeah. And so there we have it. We have the city danger zone map. And the cool thing is that Tableau allows you to save this as a shapefile so that you can immediately export it, open it to Tableau. One thing to know, I have two. So one would be all of my meteorite hits, and one is the trade zone. You can only export one as a shapefile at a time. So if you wanted both, you would have to do both of these steps and then join them into Tableau. I've chosen to just go with my trade zones and to ignore all the individual iterations. Danger zones. Danger zone. And so here, if I just go directly into Tableau, open city danger zone, should work. And there you can see all my data straight away. So the geometry, that's that shapefile so that I created, everything else, and my clusters. So if I just go and pull this into a map, I have every single trade area. Please ignore the fact that there's a giant one in North America. I don't really know why it did that. I mean, it counted them correctly, but it just made a giant, I don't even know, like rectangle going across the whole of Canada.
Maybe some bounced.
Do you need to put city in the detail? Country and city on the detail to have, to have the geometry break up more? Or is it automatically?
You mean if I put it onto detail here?
Yeah, does that
it doesn't.
fix it?
So yeah, the problem with the
So when you
shapefile
put
is that,
geometry on there, it automatically does it at the lowest level.
yeah, exactly. So now if I just want to add in my clusters, so I'm turning it to discrete,
So treat the whole thing as
put
one
that
line.
in color. So now I can see all my clusters. So of course there's too much data on the map, so you can't really see it that well. But now if I just filter by my clusters, so let's just keep only my worst ones, so the ones that have the largest number of actual asteroid hits and the largest asteroids themselves. I'm left with just these three little ones. So if I put city on label, I can see that pretty much if you don't want to open a factory in Barstow, Mariestad, or anywhere in Kenya. So yeah, that's pretty much it. So
Triangle too.
yeah, it is. Yeah, maybe it's the Illuminati. Who knows?
And it goes right through Bermuda.
And if we had maths, you know that Barstow is definitely the worst one to do anything ever.
Between Vegas.
Is it?
It's on the main.
Is it a death trap? Would you recommend it to anyone?
Alien jerky.
Yeah. Yeah, pretty much. That's on 10 minutes to go from
That's a great
stupid ass question to building which city in the world has the most asteroid
Good
hits.
job. That was great. All right. I think, all right. So Benedetta is leaving. Any questions in the room before we cut it off? No? All right. Well, for those of you that joined online, thanks for joining in. We'll put a recording of this up, and we'll talk to you guys later. Bye.
Bye.